So, we have finally reached the end of geometry. Or is it? So this video is on quadrilaterals. Now, an introduction to quadrilaterals, the word quad over here means four. So, it means four, and laterals means lines. So, basically, we are talking about a shape that has four lines. So it'll look something like this. 1, 2, 3, and 4. And you see this perfect quadrilateral right here. And that's what we're going to be dealing with. Now, we have a whole bunch of quadrilaterals that we have to deal with. And I'm going to try and do it in a way that you can actually clearly understand. And there's actually a lot of sequences to understand all the properties, because there is a lot of properties to know. And I know it's overwhelming because you probably got like a page of a whole bunch of properties, and it's like basically like 20 or 30 properties to learn. But the thing is, here's the secret. You shouldn't be learning them. You should actually be practicing them. And I'll actually show you in this video, step by step, how we get these properties and what they look like. And it'll actually become more clear as you go further into this video. So let's actually start with this. Let's go to the first quadrilateral. So our first quadrilateral we are dealing with is a square. Now this is, you guys should know what a square is at this point. We've been learning it ever since the beginning of time, the beginning of school. So a square, now we actually need to go into detail. What are the properties of a square? So this is the sequence where we are going to follow, right? This is how we're going to be listing the properties. We're first going to be speaking about the sides. So I'm going to write it down here. We're first going to be comparing the sides, the length of the sides. So it's going to be the side length. So we're going to be comparing the side length. And then our next one we're going to be comparing is the parallel lines. So we're going to be dealing with the parallel lines. And then our third one we're going to be dealing with is going to be the angles. And then our fourth one, I'm just going to write it here. Our fourth one we're going to be dealing with is going to be the diagonals. So the diag, I'm gonna be writing it as diag for short, so that you understand what I'm talking about. So this is the steps we are going to take in order to actually find out what are the properties of these quadrilaterals. So please write this down if you have to, and then you'll actually see that I'm going to constantly follow the sequence throughout the video. So our first one is going to be the sides. Now, what do the sides look like? What are the length of each sides? So in a square, we know over here that according to the properties, we have every single side of the square is going to be equal in length. And that is what these symbols indicate, that all the sides are equal in length. So that's what we're going to be writing over here. We're going to write that all sides equal in length. Can I extend this? Okay, great. Okay, now we have our next property. What did I say we're going to look at next? We're going to first look at the sides, then we're going to look at the parallel lines. Okay, so we need to look at which ones are parallel. So we can clearly see that this line over here is parallel to this line here, because they're moving in the same direction. They're both horizontal, basically, and they're going in the same direction if you were to look at the arrows. And now we also need to look at the other sides, because the other sides are not parallel, which are the vertical lines. We can clearly see that these lines, though, the vertical lines, are parallel to each other instead. So what can we write down as our property over here? We can write down that two pairs of opposite sides are parallel. Okay, now our next property we're going to look at for this square is going to be our angles. Now, where are our angles? Over here, as you can see, every single corner, our property of our square says that every single angle of the square will be equal to 90 degrees. And what do we say about this? How do we write this reason down? Or this property down? We can say all angles, so I can just quickly do it like this to make it look cool. All angles, that is not what I wanted to do. Man, this thing's going crazy. All angles equal 90 degrees. All angles equal 90 degrees. Then our last property we're going to be dealing with is the diagonals. And note, I'm actually going to be doing the diagonals in red. So I'm going to just try and draw a straight line here. It's not working. Come on, just do work with me now. So I'm going to try and draw a straight line here so that this is basically diagonal. Okay, because it's not coping with me right now, I think we are going to just assume that this is going to be diagonal here. No, I'm joking. We're not going to do that now. We're actually going to show that these are diagonal here. We're gonna challenge this thing here. Okay, I'm joking. It's not going to work. Okay, let's just assume that line touches the corner, and then this line over here is also going to touch the corner. So let me just try and draw it like this. Okay, cool. So there's our diagonals. We know what diagonal lines look like. But what do we know about these? All of these diagonals meet at 90 degrees. So we can say it over there, right? But that is not the main reason that we have. But we can write that down. We can write down that the diag meets at 90 degrees. And then our next one will be the diag will bisect each other. Now, what do I mean by bisect? The word bi means two. And then the word sect means cut. So what they are trying to say is that we are actually going to cut in half, cut into two sides, basically. And what do they mean by that? These two diagonals meet or bisect each other such that this line is equal to this line, and because we're in a square, this line will also equal to this line. Therefore, every single line over there is equal to each other, and the diagonals bisect each other. So that is all the properties for a square. If you follow this path in order to determine which one of them are, just to first deal with the sides, the length of the sides first, and then the parallel, whether they are parallel, which lines are parallel. Then we deal with the angles, and then we deal with all the diagonals. What is going on with the diagonals? That is our steps. This was the square. Let's move on to the rectangle. So our rectangle has kind of the same properties as the square. So let's just go through each of them again. So let's look at the sides, right? We can see that this side over here is the same as this side over here. But this side here on the vertical is not the same as the horizontal lines. But we can actually say that this side here is actually equal to the opposite side over here. So therefore, what our reason will actually be is let me try and get rid of the bold quickly and make it a little bit smaller here. 2 pairs of opposite sides are equal. And that is what these properties say. Let me see if I can try and squeeze this in over here. There we go, great. Okay, let's look at our next property. We spoke about the length of the sides. Now we are going to speak about the parallel lines. Now, where's the parallel lines over here? What we can see is that this line over here is parallel to this line over here, the opposite line. But obviously, the horizontal lines are not parallel because they're horizontal, and the other ones are vertical. So we can see over here that this line over here is going to be parallel to the opposite side, which is this one here. And how we're going to write that down? To no surprise, it's going to look exactly the same as the length one, but now we're going to say 2 pairs of opposite sides are parallel. Note how I'm going to write parallel like this, with the 2 dashes, or the 2 forward slashes, because it's easier for us to see. That's what our parallel actually is in symbols. Okay, what's the next thing we're going to look at? We're going to look at the angles. Now, where are the angles? Here we're going to have the angle over here, which is 90 degrees, we can see. And then we're going to have this angle over here, which is 90 degrees. We're going to have this angle here, that's also 90 degrees. And this angle here is also 90 degrees. So therefore, we can say that our property for the angles is that all angles, let me try and be fancy here as well, all angles equal to 90 degrees. All angles equal to 90 degrees. Now we have our last reasons over here, which is what we're going to be working with is going to be the diagonals. Now let's try and do the diagonals this time here. Let's see if we can actually get straight line, beautiful straight lines here. Okay, there we go. So we got a diagonal over here going from one corner to the other corner, and then we got another diagonal going from one corner to the other corner as well. Okay, so now as you can see, the difference between the square and the rectangle is that these angles are not 90 degrees, because you can clearly see that this angle over here, these angles are different in length. They're not the same length. But as we can see, obviously, that this angle here is equal to this angle here because of vertically opposite angles. And this angle here is also equal to this angle over here because they're also vertically opposite to each other. Okay. And then when we look at our lines, or to be specific, our diagonals, we can see over here that these diagonals bisect each other such that this side is going to be equal, this side is going to be equal, this side is going to be equal, and this side is going to be equal. So what we are going to say over here is that, or it was right here anyway, that the diagonals bisect each other, and then that is what we are going to say over here. You don't really have to include the length or equal. The length is equal, but you can say the diagonals bisect each other such that the lengths of the diagonals are equal to each other. But for now, we can actually just say diagonals bisect or diagonals bisect each other. And those are our properties of the rectangle. Let's move on to the next shape. So our next shape is now a rhombus. So let's look at them again. Let's compare this. Let's look at the properties. Now let's look at the sides. So with the rhombus, we now have to know that this side is equal to this side and is also equal to this side and is equal to that side. So what we are talking about, when we are talking about a rhombus, we are going to say that all sides are equal. And now for the next one here, what we're going to look at is going to be the parallel lines. So we can now see that this line over here is parallel to this line here, opposite to it, because they're both diagonal in the same direction. Then this line, which is horizontal, is parallel to the other horizontal line, which is opposite that line over here. So now what we can say is that two pairs of opposite sides are parallel. Okay, now we can move on to our next property. We are going to look at the angles, right? What we need to know about a rhombus is that this angle here, or let me write it like this angle here, this dot, is going to be equal to this angle here opposite. And then this angle here is going to be equal to the opposite angle, which is also here. And as you can see, that this angle here is obtuse, and this angle is also obtuse. And this one is acute, and this one's also acute. So that's how we can also notice that those are going to be equal. Oh, but only if they state it's a rhombus, then we know that's true, because we are given these properties, but I'm trying to show you how to actually get to these properties without just remembering them all the time. It's actually good to practice these things. But anyway, I can stop yapping. Here we have two pairs of opposite angles. So I can write it here. That is, whoa, that is not what I wanted to do. I can say over here of, so angle, two pairs of opposite angles are equal. I don't even have to say are, equal. Now our last one we are going to look at is the diagonals. So let's look at the diagonal here. Here, there's where the diagonals go, and then this diagonal here will intersect with the other diagonal, like that. Okay, so what do we see over here, right? Because this is a rhombus, we must know that all of these angles are 90 degrees. These diagonals will meet at 90 degrees. So that is what we're going to say over here. So the diag meet at 90 degrees. And then our next one over here, let's look at this. This is the difference now. Because we have a rhombus and because we have diagonal lines, and also because we have different angles, opposite angles over here, two pairs of opposite angles, these two diagonals will bisect each other, but leaving these two lines different in length over here, which is because of the angles represented in the rhombus, the two pairs of opposite sides. So this line will be equal to this line, but this line over here will be equal to this line over here. So that's the only difference there. So how do we write that down? We say diag will... No, we don't write that down. No, the diagonals, sorry, will bisect each other. Almost started contemplating. Diags bisect each other. Okay, now that is our properties of a rhombus. Now let's move to the next shape. So here we have a parallelogram. And in brackets, I showed that how you can actually write it. Whenever you're doing reasons, you either say the parallel symbols, or you with the M obviously over here, or you can actually do the following. You can say parm, P-A-R-M. This is what other people do it differently. You don't have to do it like the other, whichever one does better, you can actually use that. But I use the parallel lines with the M because it's easier and quicker, and I'm lazy. Okay, so now what do we know about the properties of a parm? Or you see there, I'm doing it now, a parallelogram. So what we can say over here, we first have to look at the sides. So if we look at this side over here, this side is going to be the same as this side over here. But this side over here is going to be equal to the opposite side over here. So what we can say is that it's kind of the same as a rectangle here, but now it's a parallelogram. It's like a skew rectangle in this case. It's a rectangle with two diagonal lines now. So we can say over here, oh yeah, I also apologize. These lines are the same. These need to be here, there as well. Because all of the lines are not the same in length. And that is how we represent it now here. Okay, so we say that two pairs of opposite sides are equal. Okay, now we're going to look at the parallel lines. Where are they parallel? We can clearly see that this line here is parallel to the opposite line here, because they're both diagonal in the same direction. And then this line here, which is horizontal, is parallel, and this opposite line over here is also parallel because this one is also in the same direction. So we can say over here that two pairs of opposite sides are parallel. Okay. Next one, we're going to be looking at the angles. So now what we need to know about the parallelogram is that there's two pairs of opposite angles that are equal. So this angle here is equal to this angle here. I'm representing it as dots. And then this angle here is going to be equal to this angle over here. And therefore we can say over here that two pairs of opposite angles, be nice, come on. Okay, angles are going to be equal. Okay, now our last one we're going to look at is the diagonals. So now, if we look at the diagonals, we can see over here that this diagonal goes from this one point to the last point over there, and then this diagonal goes from this point over there all the way to the next point over here, which is opposite. Okay, now let's look at these lines over here. Now what we can see over here is that this angle here is the same as this angle over here. Also, I know there's also dots, but the different color indicates we're working on something different. So don't compare this dot over here to this dot over here. I'm doing it in a different color for a reason, because there's too much information, and I think if I do it in a different color, it's easier to actually point out the difference. So just bear with me with this color changing thing. And then this angle here is equal to this angle over here, because remember, they're vertically opposite to each other. So now what can we say over here about the diagonals? The diagonals, once again, they always bisect at this point, but not always actually. These diagonals bisect such that this line over here is equal to this line, but because we're working with a parallelogram and because we have two pairs of opposite angles that are equal, these lengths will actually be different. Okay, so we can now say over here that the diag bisects each other. And that is what we can know about the parallelogram. Let's move on to the next shape. So the next thing we have is a trapezium. Now take note, there's actually two types of trapeziums that we have. There is okay, hold on. Let me actually just do this one first. So the first one we have is an isosceles trapezium. So, that is not grabbing that one. Okay, so this is our isosceles trapezium. Now I'm going to show you why this is an isosceles, and I'm going to use reference to the isosceles triangle, which we already know about. So first, let's look at the sides. We can see that this side over here is clearly not the same as this side over here, opposite that side over there, because that one on top is shorter than that of the bottom over there. So now we can clearly see that those are not equal, but the sides that are equal is going to be these ones over here. This side is going to be equal to this side over here, and therefore our reason over here will be one pair of sides are equal. Only one pair of sides are equal. So I'll say only one pair of sides are equal. Okay, what's the next one we're going to be looking at? We're going to look at the parallel lines. So now as you can see, this line over here is not parallel to that line because they are diagonals, right? But they're not in the same direction as each other when they normally move. At some point, if you draw the lines even further, and then you're going to clearly see that they are going to touch each other. They're gonna intersect at some point. But let's now focus on which line is parallel. We can see that the top line over here is in the same direction as this other opposite side over here, the horizontal line. Therefore, we can say over here only one pair of sides. Sides are parallel. Our next one here we're going to be looking at is going to be this. Because we have an isosceles trapezium, if you remember from a isosceles triangle, we know over here that this side over here is actually equal to that side over there. The two adjacent sides are equal, such that these angles here, or this angle here, is equal to this angle over here. Now, what we know about isosceles trapezium is we can say the same thing over here. We can say that this angle here is actually the same as this angle over here, because only in an isosceles trapezium. And then we can say over here, instead of only two opposite sides being equal, we have over here this side over here and this side. these sides are equal to each other. So therefore, we can say over here that two pairs of angles. Okay, I know we're not going to say opposite angles because they're not technically opposite each other. Because if we are talking about opposite angles, we are basically talking about that angle is opposite to this angle is opposite to that angle, and this angle is opposite to that angle. And those are not opposite angles. So what we are just going to say is two pairs of angles. Yeah, it's that. It's just like that. Angle are going to be two pairs of angles are equal. Okay. Now we're going to look at one more reason over here. Or one more property. Remember, now we have the diagonals. Now the diagonals, let's draw our diagonal over here. It's going to go until that point over there. And then this diagonal at this point will go all the way until the diagonal over here. Okay. Now what can we see over here? If we look at the diagonals, we can now see, obviously, that this angle here is going to be equal to this angle over here because they're vertically opposite. And the same with these two angles here. Now, let's look at the lengths. When we are looking at a trapezium, we can now see that the length of this side over here is equal to the length of this side. But now, this length is now equal to this length as well. Now this has come to my attention here. These diagonals do not bisect each other. As you can see, that this length, normally if they're bisecting each other, right, this line would normally cut through this line in half, right? It will cut this line in half. But you can clearly see if it does cut it in half, then these two lines would actually be equal, but they are not. So therefore, what we can say, I know this is just extra, you don't have to do this, but at the same time, it's cool to write this down. Diag do not bisect each other. Diagonals do not bisect each other in an isosceles trapezium. Now let's do another trapezium, and I believe it's going to be a normal trapezium in this case. So this is probably the most amazing shape that you'll ever see in your life. So this trapezium over here, let's look at the lengths. None of the lengths are the same. So that is what we know about the trapezium over here. No sides are equal. And then we look at the parallel lines. Which lines are parallel? Now we can clearly see only these lines are parallel over here. These two horizontal lines. So therefore we can say only one pair of sides are parallel. What's the next thing we can see? Let's look at the angles. Now we have, okay, I'm not gonna lie, there are no angles that are equal, but in one of these examples I only have this and this. So I don't think they really give these trapeziums in questions, and that's why I'm thinking I've never seen a trapezium like this ever. But those two angles only look like they're 90 degrees. So let's not focus on the angles right now. So we're actually going to only look at the parallel lines and the sides. And now, what else can we say about the diagonals? The diagonals, if we were to do the diagonals, and the thing is none of them are going to be bisecting each other, and none of them are actually going to be the same. So I think it's actually worth leaving out in this case. So that's why a trapezium is actually probably one of the normal trapezium, with like not the isosceles one, is actually very, very just exists. But we don't really work with this one. But it's cool to know that only one pair of opposite sides are equal, and no sides are equal to each other. Let's move on to the next shape. So our second last quadrilateral that we're going to be working with, and the last one is actually a special one. I wanted to save that for last, so I can explain what on earth is happening with quadrilaterals. But for now, let us go over the kite. So let's look at the sides. The sides that we are comparing are these adjacent sides over here. And if you remember, adjacent just means that the sides beside each other or next to each other. these two sides over here that are adjacent to each other are equal. So therefore we can say two pairs of adjacent sides are equal. And then I can just extend this because it can actually go further. Okay. Now, the next thing we are going to be looking at is going to be the parallel lines. Now, what we should know about the kite is that there is no parallel lines. They're all in a different direction. None of the lines are parallel. So here we can say that there are no parallel lines. No sides are parallel. Okay. Now what are we going to look at next? We're going to look at the angles. Now what I can actually do, right? I can say this, right? That this angle over here is going to be equal to this angle over here. And these angles over here will actually be equal to each other. But now what we can say over here is that one pair of opposite angles are equal. And now we're going to talk about the diagonals. Now okay, but it's not necessarily diagonals, but in this case we're just going to call them diagonals because we've been doing that now we've been doing that a lot now. So here there's that diagonal, the so-called diagonal, and here's the other so-called diagonal. Okay, so what can we see over here? I want you to just realize what we have over here. We can see that these lines will intersect through each other such that these angles are all 90 degrees. So what we can say over here is that the diag meets at 90 degrees. And then what else we can say over here? That this side over here is equal. So then we can say that only one diagonal will bisect, which is going to obviously be the diagonal going from top to bottom. It bisects the horizontal line. And something cool that you can actually see from this, you don't have to write it down as a property, but it's also cool to know that because we have these sides over here, and we can see that this whole thing is a triangle, this whole shape is just a triangle, it's just an isosceles triangle. So we can say that this angle here is the same as this angle over here, and we can also see we have another isosceles triangle, but it's upside down. So therefore, we can say over here that this angle here is equal to that angle over there. That's just some cool information to know as well. Okay, and now we're going to go to our last shape, and it's not really a shape, but like at the same time, I just wanted to add it to this video to actually indicate what are quadrilaterals normally used for in geometry, Euclidean geometry. So here's our last quadrilateral, and this is the irregular quadrilateral. Now, as you can see, there is no sides that are equal in length. There is no sides that are parallel to each other. The angles are not all equal to each other. Assumption made. And the diagonals are useless in this case. There's nothing special about the diagonals, but obviously that is what an irregular. That's just also cool to know. But at the same time, I wanted to use this as an example. I wanted to let you know that the properties of a triangle over here, or sorry, not a triangle, a quadrilateral, that all of the angles, so let's say it's going to be this angle over here, x, for example, we don't know what it is, and this angle y, and this angle w, and this angle z. All of these angles will equal to 360 degrees. Now remember, whenever we worked with the triangle over here, the angles will always equal to 180 degrees. But that is when you're adding all those three angles over there. Now, as you remember from our rectangle or square, remember that we had all 90-degree angles in that case. And if you add all the 90-degree angles, if you just say 90 degrees times 4, then you're going to get about 360 degrees. And that is going to be the same for the square and every single quadrilateral. So therefore, the sum of all these angles over here and here and here is going to be equal to 360 degrees. So that's our main properties. So I'm going to say over here, main properties. We're going to say the sum of all angles in a quad equal to 360 degrees. Equals to 360 degrees. And that is what we need to know about these quadrilaterals. And then, yeah, this is the main property actually. I want to just state that. Okay. Now, with the rest of the questions, if we're answering questions on quadrilaterals, we just need to obviously consider that we need to know our properties. And then we also need to sometimes they even integrate or combine triangles. They combine triangles to actually form quadrilaterals. Normally they would form like either 2 triangles or 4 triangles to give you a quadrilateral. And then you need to actually do similarity and congruency to answer those questions. So I want to end off this video here, and in the next videos for geometry or Euclidean geometry as a whole will now only be focused on examination-based questions or practical questions that are sent by my students. So I want to just state that now we have finished Euclidean geometry so far for grade 9 at the moment. There's going to be more coming later on or next year. But for now, these are the basic Euclidean geometry reasons that we needed to know for each shape, like straight lines and then triangles, and now lastly quadrilaterals.